Chapter 5, Section 3 starts with a reminder of the definitions of our 6 trig functions that we explored in the previous section. Now notice that we point out that these definitions are for where we are on the unit circle, so that sine theta is just equal to y. This is true because on the unit circle, r is 1. So when I have sine theta is y over r, that becomes y over 1, or just y. And that's true for each of the definitions of our trig functions where we would have an r, that r is just 1, and so it doesn't affect our function value. Now, this page is going to help us to explore the domain and range of each of our 6 trig functions. Think back to college algebra. When we graph functions in college algebra, we started out by talking about whether the function was continuous over its domain or if it was discontinuous, what values needed to be left out. So we're going to address those same things for our trig functions. Use these definitions to help you make conclusions about the domain and range of the functions. Make sure you know what variable is in the domain, what is the input, and what the variables are in the output. Well, first of all, for all of these angles, as long as we're talking about the function, the input is going to be the angle, and the output is the function value. So for sine theta, where we start, sine theta, and I'm going to go ahead and kind of delineate one from the next. For sine theta, our input is our angle theta, and our output is y, which is the sine function value. This means that the domain of the sine function is all real numbers. I can include any value, any angle, to find a sine function for it. The range is from -1 to 1. Now think about this. Even if I'm not on the unit circle, I would have sine theta equals y over r. Well, r is the radius of my circle, which becomes the hypotenuse if I were to drop that perpendicular and form the right triangle, which means r is always going to be the longest side. Now, there's a potential that it could be equal to whatever y is, but r is always going to be at least that long or longer. So what I'm going to end up with is a value of y that has to be equal to r or less than r, which gives me that range value from -1 to 1, no matter what r is. This is true for the unit circle, but it's also true for any circle. Let's talk about cosine. For cosine, the input is theta, and the output is that x value. If I'm on the unit circle, it's x over 1. If I am not on the unit circle, again, it is x over r. This means that the domain of the function, of the cosine function, is still all real numbers because I can plug in any angle. And the range is going to be between -1 and 1 because that ratio of x over r is always going to be 1 or less, positive, -1, or between that. Okay, what about tangent theta? Well, tangent theta looks a little different because I'm not comparing something to the radius this time. So we've done sine, we've done cosine. Now let's switch and do tangent. For tangent theta, the input is theta. We're still inputting the angle. That does not produce division by 0 because the radius is no longer our denominator. Now the denominator is going to be x. We need to only use angles that do not give us a value of 0 for x. This means that the domain of my tangent function is limited. I have some restrictions. It's all real numbers except odd integer multiples of pi half, or 90 degrees. Well, why odd integer multiples of pi half? Well, because of those odd integer multiples of pi half. So that's going to be here and here. 1 pi half, 3 pi halves, 5 pi halves, 7 pi halves. Or if I rotate clockwise, the negative values, the odd pi halves. At those values, my x-coordinate is 0. I've got a y and I've got a negative y, right? So at those values, tangent of the pi halves is undefined. So at tangent theta, where theta is one of the multiples of the pi halves, you get y over 0, and that is undefined. So we have restrictions there. Well, what about cotangent? Does cotangent have the same set of restrictions? Is it undefined where x is 0? For cotangent, the input is going to be theta, and the output is going to be x over y. So now my y is in the denominator. That means that my domain has to be restricted to those places where y is not 0. Well, where is y 0? Well, y is 0 on the x-axis, so it's going to be at those full values of pi. So we're going to say that we restrict the domain of the cotangent function to all real numbers except where y is 0, which is all of the integer values of pi. So y is 0 here and here. This is going to be x 0, and this is going to be an x and a 0. So at 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, etc., cotangent would be undefined. Now, we didn't talk about the range for tangent. Tangent compares y to x, and y and x can be anything. We can have any measurements on the x and y axis that we want. There's no restrictions there, so they can be so that my numerator is huge and my denominator is small, or vice versa, which means the range of tangent is all real numbers. That's going to be true as well for the range of cotangent, because we've got x compared to y, so cotangent can be anything. All right, cosecant and secant. Cosecant is the reciprocal of sine, and secant is the reciprocal of cosine. Remember those. The C goes with the S, the C goes with the S. Okay, for cosecant, the input is any angle theta. So I'm always inputting an angle, getting out a function value that does not produce division by 0, and the output is 1 over y. Or, if I'm not on the unit circle, r over y. This means that the domain of the cosecant function is all real numbers except, well, where am I going to have y values that are 0? That's going to happen. Right here, like we said with our cotangent, where we have y in the denominator at those integer values of pi. And except integer multiples of pi, 180. So all real numbers except integer multiples of pi. And the range is going to be all real numbers greater than or equal to 1, less than or equal to -1. Now, I want you to think about this in terms of it being the reciprocal of sine. Because it's the reciprocal of sine, reciprocal of sine, and the range of sine is -1 to 1, therefore, for cosecant, the range is going to be everything else. So when I flip that, I am including what's in between from -1 to 1. But when I flip from sine to cosecant, I take the reciprocal, that range flips and goes outward. So instead of everything in between here, it's going to be everything else. -infinity up to -1, or +1 to +infinity. So here I have the middle. When I take the reciprocal, I have the ends. Instead of y over r, now I have r over y. because cosecant of theta is r over y. Remember what we said, the r is always going to be at least as long as y, usually longer. So I'm going to start by having that absolute value of 1 and then going up so that r is larger than y. Then we have secant as our last one to address. Secant is the reciprocal of cosine. Because we're finding secant theta, we're inputting an angle, and the output is going to be 1 over x for the unit circle, or r over x for any circle. This means that the domain of the secant function is going to be anywhere x is not 0. So if I go back and tie it, I can tie it back to the same as the domain of tangent, because my tangent function also has an x in the denominator. The domain is going to be all real numbers except k pi halves, where k is an odd integer. So in the odd half iterations of pi. And the range, just like cosecant, because it's the reciprocal of cosine, cosine has that range in between -1 to 1, I flip it. The range is going to be from -infinity up to -1, or from +1 all the way to +infinity. Now these domain and ranges, understanding these and being able to reason through them and remember what they are is going to be very important as we move forward. So make sure that you understand how to get there and what they are going to be. Let's look at the exploration number 2. Determine the period of the trig functions. So from 5-2, we saw that sine of 5 pi is equal to the sine of pi, and both of those are 0. Well, why is this the case? The sketch, I think, is easiest to explain. If I am rotating 5 pi, I would say 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and stop here. Well, 5 pi lands at the same place 3 pi and 1 pi end, and the sine function value is the y coordinate, that is 0, while you're on the x-axis. Based off of this explanation, if I start at if I start at theta, and I rotate another full rotation, 2 pi k, however many rotations I want to go, where k is any integer, that is going to be equal to the same thing as if I were in degrees, because 2 pi is the same thing as 360 degrees. That's going to give me the same sine function value as just theta, because this location is the same as pi. It has the same sine function value as at pi. And equally, for cosine, as I make any number of rotations and I terminate at the same place, it's going to be equal to just the cosine of theta. Now, these are our angles of rotation. We talked about this already when we talked about rotating through and where we are coterminal. Functions that exhibit this kind of behavior, where you can add or subtract something to the angle measure and the values are the same, are called periodic functions, because all the values repeat over a certain period. For sine and cosine, that period is 2 pi, a full rotation. We come back to the same function value. A function f is called periodic if there is a positive number p, such that whenever theta is in the domain, so is theta plus that period. And the function value of theta plus that period is going to be the same as the function value of theta, because they terminate in the same place. If there's a smallest such number p, that is the period of the function. So based on this, the period of the sine function is 2 pi, which is the same thing as 360 degrees, and the same is true for cosine. Now, just like sine and cosine, they're reciprocal functions. The sine has a reciprocal function cosecant. Cosine has the reciprocal function secant. They are also periodic over 2 pi. Their sine and cosine function values are going to repeat after every full rotation. Now, tangent and its reciprocal function, cotangent, repeat more frequently. We will find that they are periodic over pi, that at every 180 degrees, their function values repeat. That is the smallest possible period before those function values begin to repeat. Okay, using this fact that trig functions are periodic, find the value of each expression. So what we're trying to do is find the smaller positive angle that is coterminal so that we can use our special angles on our unit circle to predict the exact function values. For example, 390 degrees. Well, if I subtract 360, I see that I have 30 degrees. So if I were thinking about drawing this, to get to 390, I would go a full rotation plus 30 degrees more. That's going to be 390 degrees. A full rotation plus 30 degrees more. 390 degrees is coterminal with 30 degrees. And I can either remember or look at my unit circle and determine that the sine function value at 30 degrees is 1/2. So that is also the sine function value of every angle that is coterminal with a positive 30 degrees. So what we're doing to solve this is to find the smallest positive coterminal angle. Smallest positive coterminal angle. Okay, tangent of 19 pi fourths. Well, we're in radians. A full rotation would be how many fourths? Well, 2 pi is going to be 8 pi fourths. And if a full rotation 2 pi is 8 pi fourths, how many of those full rotations can go in here? Well, 8 pi fourths times 2 is 16 pi fourths. So if I subtract 2 full rotations, I see that 19 pi fourths is going to be coterminal with 3 pi fourths. And 3 pi fourths is my 45 degree angle in quadrant 2. So I have 1 pi fourth, 2 pi fourths, 3 pi fourths. 3 pi fourths is going to be right here. It's also going to be the same as there's 1 rotation, 2 rotations back here as 19 pi fourths. So what is the tangent function value at 3 pi fourths? Well, tangent is sine over cosine, and at the 45s, they are the same thing. So it's either 1 or -1. If I'm in quadrant 2, that tangent function value is negative because x is negative and y is positive. All right, next page. Exploration number 3 excuse me, asks us to determine the sign of the trig functions in a given quadrant. Okay, so let's think about this. It says to complete the graph with the appropriate algebraic signs of the ordered pairs. S-I-G-N, not S-I-N-E. So we're gonna label that as algebraic signs. In quadrant 1, and it gives us parentheses, but they're too small. In quadrant 1, both x and y are positive. In quadrant 2, x is negative, y is positive. Down here in quadrant 3, both x and y are both negative. And then in quadrant 4, we have positive x and negative y. Well, how does that pair up? Knowing the relationships between the ordered pairs and the trig functions as seen in the last section, we can find the appropriate sign for each of the trig functions. So we're going to pair them up and talk about where they go. We're going to start with sine and cosecant. Now, sine and cosecant, if I'm on the unit circle, I just have y. If I'm not on the unit circle, it would be y over r and r over y. So I'm interested in what y is. Well, y is positive in quadrants 1 and 2, and y is negative in quadrants 3 and 4. So both sine and its reciprocal cosecant will be positive in these two quadrants and negative down here. Now, cosine and its reciprocal secant don't depend on the y, they depend on the x. They are x dependent. So we're going to be interested in the algebraic sign of the x coordinate. Well, x is positive over here in quadrants 1 and 4, and x is negative over here in quadrants 2 and 3. So those are also the function value signs, positive or negative, for sine and cosecant, because they depend on x. X over r for cosine, and r over x for secant. Again, if I'm at the unit circle, that r is just 1. And finally, we have tangent and cotangent. Now, tangent and cotangent use both the x and the y. They refer to both of them. So we're interested in, are the x and y, do they have the same algebraic value? Are they both positive, both negative, or do they have different signs? Are they one positive, one negative? Well, in quadrant 1, x and y are both positive, and in quadrant 3, x and y are both negative. So positive over positive is positive, negative over negative is positive. But in quadrants 2 and 4, the signs, algebraic signs, are different. If I could use a plus and a minus, I get negative function values. Okay, using this information, we want to find the different quadrants in which the given angle is going to fall. So we want to think about an xy coordinate plane. Name the quadrant in which angle theta lies if sine of theta is greater than 0. So sine of theta is positive and cosine theta is negative. Well, where is sine of theta positive? Sine of theta is positive where y is positive, so quadrants 1 and 2. Cosine theta is negative. Well, cosine theta is negative where x is negative. X is negative in quadrants 2 and 3. Where are both of those things happening? Right here. So the answer is quadrant, I marked it right and said it wrong. Quadrant 2. My answer is quadrant 2. An angle where both of these happen is going to always fall in quadrant 2. Let's look at the next page. Based on our earlier definition of the 6 trig functions, we can now establish the following trig fundamental identities. Now, these are things that we have been talking about all the way through, but we are listing them as specific identities. First, we have our reciprocal identities, that cosecant theta is the reciprocal of sine theta, secant theta is the reciprocal of cosine theta, and cotangent theta is the reciprocal of tangent theta. This is true given our definitions. We know that sine theta is y, and cosecant theta was defined as 1 over y. Therefore, cosecant theta is equal to 1 over sine theta. And since sine theta is y, we have 1 over y. 1 over y. 1 over sine theta, because y is the same as sine theta. And then you could write a similar statement for the other two. Then we have our quotient identities for tangent and cotangent. Why is this true? Again, by definition, tangent theta is defined as y over x. We know that sine theta is y and cosine theta is x. Therefore, if I substitute, I get that tangent theta is sine theta over cosine theta. Now, I started by introducing these things to you that way, so you already are aware of them, but now I've given you names for them as far as the types of identities we're using. Example 3. Given that sine theta is equal to square root 10 over 10 and cosine theta is equal to 3 square roots of 10 over 10, find the value of the 4 remaining trig functions of theta. Okay, so we know sine and cosine. The next one we're going to find is going to be tangent. Our 3 main trig functions are sine, cosine, and tangent. Then we have the reciprocals of those. So let's do tangent theta. Tangent theta is sine over cosine, so square root 10 over 10 over 3 square root 10 over 10. Those 10s are going to cancel out when I think about using dividing fractions by multiplying by the reciprocal. Those 10s in the denominators cancel out. That leaves me with square root 10 over 3 square roots of 10, which simplifies to just 1/3. So now we need to find our 3 reciprocal functions. Sine theta is square root 10 over 10, so cosecant theta is the reciprocal of that, 10 over square root 10. I need to justify that, rationalize that. So I'm going to do times square root 10 over square root 10, which gives me 10 square root 10 over 10 and simplifies to the square root of 10. Then secant theta is the reciprocal of cosine, so I take 1 over cosine, or just flip that value, rationalize again, and I get square root 10 over 3. And then finally, cotangent theta is the reciprocal of tangent. That one's just 3. All right. One of the major things you need to get used to doing is working with these trig function values, starting with what you're given and figuring out what you need to answer the question that's being asked. For this one, we're given the value of sine. We're told that our angle falls between pi and 3 pi halves. Well, pi and 3 pi halves, that defines quadrant 3. In quadrant 3, what is true? Well, in quadrant 3, both x and y are negative. So that gives us a little bit of guidance. If x and y are both negative, sine is negative, cosine is negative, their reciprocals are negative, but tangent and cotangent are positive. So we know the algebraic sign of our 6 trig functions. We need to find the values. We're going to start here. Sine theta is -2 over 3. That means that my x-coordinate is -2 and my y-coordinate is not 3. I'm sorry. My x-coordinate is -2 and r is 3, and we need to find the y-coordinate. My x-coordinate is -2. That is just not right. I'm doing this all backwards. Guys, this is where I really, really miss you guys being in the classroom and pointing out to me, no, that's not working. So sine is y over r. My y is -2. My r is 3. So y is -2, r is 3, and I need x. X is what I'm looking for. Good grief. Now, let's think about what I did wrong. I started out, first of all, going top to bottom, and I wasn't paying attention. So I wanted to say this is x, this is y, and then I realized, no, that's not y, because I've got sine, this denominator is r. But because I have sine, my numerator is y, not x. So I just totally was not paying attention to start with. If we have a y-coordinate of -2, an r-coordinate of 3, we're looking for our x-coordinate. So x we don't know, y is -2, r is 3. Because of our Pythagorean theorem, this says equation of a circle. X squared plus y squared equals r squared. That works as well. So if we use our Pythagorean theorem or equation of a circle, whichever way you want to look at it, we don't know x plus y squared equals r squared. Well, y squared is 4, so x squared is going to be equal to 9 minus 4, which is 5. To solve that, I'm going to take the square root. Now, when I take the square root of both sides, I have to think about plus or minus, but since I'm in quadrant 3, I know that I want my x-coordinate to be negative, so x is a negative square root 5. All right, despite my mistakes, we have plowed through, shouldered through. Everyone is going to make mistakes. Sometimes you learn better when you do make some mistakes, because you have to go through and problem solve and think and make sure you justify your conclusions. We were given sine. We're going to find cosine theta tangent theta, and then the 3 reciprocal functions. Cosine theta is x over r. So I have a negative square root 5 over 3. Tangent theta is y over x. Negative over negative is a positive. So that becomes 2 over square root 5. When I rationalize, that's 2 square root 5 over 5. Then I move over and I find my 3 reciprocal functions. Reciprocal of sine is cosecant. Reciprocal of cosine is secant. And reciprocal of tangent is cotangent. So reciprocal of sine is cosecant. It's going to be a negative 3/2. Reciprocal of cosine is secant. When I flip that, I'm going to have to rationalize it. It becomes a negative 3 square root 5 over 5. And reciprocal of tangent, if I start before I had rationalized and just flip that, I do less work. Square root 5 over 2. Both secant and cosecant are negative because they're the reciprocal of sine and cosine. Cotangent is positive because it's the reciprocal of tangent. Our next exploration introduces one of our main